Now back to my project folder, this one. So here I am going to create another folder in which I will be saving my new project. So what is the new project? Now I need a block design, right? So into the block design I am going to add this particular IP. So I'm going to open a new project. So I'm going to select that particular folder. Within this project folder, you can create anywhere, but just to organize it properly, I'm selecting this particular project location. So inside that I'm creating another folder to save my block design. So block design project. Okay, so this is my block design project. Again, I have to select the board. It is a fresh project. Again, finish. So I will close that IM negative previous one. So it's completely a fresh project. So here what we will do, we will go with the block design, right? So I will create a block design. You don't have any Verilog code here. So in the block design, I will be using the IM negative IP. So if you search for the IM negative IP, you may not find it here. You cannot find it here. Okay. That is because you have not mentioned that repository. So you have not mentioned with the tool to look at that particular repository in which you have saved your IP. So go to settings here, click on IP repository. So here you have to add that repository. So which was our repository? This one. Okay. Select. So it has identified one IP over there called IM negative. Click OK. Okay. Now if you search for that IP, that was IM underscore negative, you can see over that. Okay, so that is already there. So we'll start in sequentially. We'll start by adding the sync mpsoc. Now go for run block automation. We'll apply the board presets. So here, let's see what all things you have to add. Let me remove one axis port here because I don't need it right now. Okay, let me remove that interrupt also, which we always do. Okay, so we are done with the block design sync part. Now what all things are required? You need your inverter, right, or your image negative module. So control I, sorry, this is control I. So IM underscore negative. Fine. So this is your custom IP that we have created. So what you have to pass here? You have to pass, the slave will receive the 32-bit data and he will perform the negative operation and he will give the master will give the negative image or negative of that particular input data. Now, are we transferring data directly from the sync? No. So you need an intermediator, that was DMA. That's why we defined it for using axis stream protocol. So I'm going to add DMA. Search DMA in this. So you can see different DMAs over there. You select this one, axis direct memory access. Okay. So this is the DMA block. Now run connection automation appeared here. Previously you have seen that even though you have added this IM negative IP, this is your device, there was no run connection automation. So some connection you have to do manually, right? So we'll look into that. Now you can see here, if you double click on this, there is a scatter getter engine here. You just disable it. We are not using that right now. Here you can control some other parameters like data address width, data width. So my data width is 30. Okay, you can go up to 1024. We are trying with 32 only. Click OK. Nothing to change over there. Now if you click run automation, some automation parts will be done. You can see that still your device is untouched. It's not connected at all. So let's see what is the issue and we'll solve it. We have to do it manually. So let's do that manually. So from where this slave will get the data? Slave will get data from the DMA. So DMA master. So you can see 3 masters over here, which is my master. These are of axis only. I'm using axis stream protocol. So this is my master. So from there you connect to the slave, right? Now Once this device will take the image negative, you can give it to the DMA back. Where you can give it? To the slave. So there are two slaves. So first one is axis light, second one is axis stream. So we are using axis stream protocol. Now that is done, you can go for connection automation. So clock will be assigned to it. Okay, so click OK. So your clocks will be now automated. Okay, clock is connected. So one clocking wizard was used. Okay, it's not required. Sometimes if you have clock issues, you have to use the clocking wizard also. Let it be there, and we will probably have some errors and we will sort it out. Okay, now the next thing is, okay, so we will have the data from the so this will be the flow from this master axis HP port. You will have ultimately the PS will be having the data. PS will send the data to axis interconnect like this. From the axis interconnect, data flows through DMA, right? Now from the DMA, the data go out from the master port. It will reach the device who performs the negative. Now once he gives the output image, output negative, not the image, a data, it will come to the DMA. Now from the DMA, it has to go to the PS. So PS, it's not going to the PS. It is not going. You have the master axis ports over here, but there is no slave port in the PS to receive that. So double click over your PS SOC, and there in the PS you have to enable PSPL configuration, PSPL interfaces, slave interface. You need an axis slave interface. Okay, I'm using the HP high performance port. Click OK. So you can see the slave interface now. Again, run connection automation is there. So what will happen when you click over there? This master will be connected to this. So both master has to be connected to this. Okay, so you need some other interconnect in between. It will not be axis interconnect. It will be some axis smart interconnect. I will show you that. So you will have see axis smart. Where is axis smart? Axis smart interconnect. So that connects this thing to the master to axis smart, and from there to the PS. Okay, so one more connection is missing. That's why the tool is identifying that. We'll connect that also. Now it's done. Okay, so through these two wires, it's being managed. The data will receive here. So we are done with all those things. Now let's validate the design. Once again, I will say the flow. From the PS, data flows through the axis interconnect to the DMA, and from DMA through the axis stream, it will reach our device. He will take the negative 255 minus data and pass it to the DMA, and from DMA through these two wires, it will reach the axis smart connect. From axis smart connect, it will reach back at the PS, and you can see it in the terminal. That's what we're trying to do. Probably we'll have some errors sometimes. Let's see. Let's validate the design, because whenever clock wizard appears, that means there is some clock mismatch. Okay, now let us try to sort it out. Now see this, it is showing that the axis stream, okay, it is using this particular frequency 99990000, and the axis M axis our IM negative, he is actually using 100 megahertz. So the thing is that if you look at the clock frequency of your PS, here you can see the clocking. If you look at the output clocks, PL fabric clock, its value is actually 100, but they are giving 100, but the actual frequency is something different. Okay, so that's why you are getting that error, and that's why clocking wizard appeared here. You can sort it without the clocking wizard also. So in the output clock, you can see that see, even though you are giving 100 megahertz, you will get only 99990000. Okay, so if you are keeping the clocking wizard, you go with this value. Okay, and if you are deleting the clocking wizard, for example, you can remove the clocking wizard. Then if you connect the clock directly, I will show you the error. Just deleting this thing also. I'm manually trying to connect the clock. So I'm going to, let's track this clock once. So this clock is coming here, but here it's not connected, right? the axis smart clock is not connected. And where is our negative? Yeah, so I will connect this clock between them manually here to here. So all clocks are connected, right? Now is there anything pending? One reset signal is pending. You can connect the reset also. Reset processing system is there. You can use any reset. I'm just connecting this. Okay, still it's identifying some unconnected port. Let us check what is that. External reset clocking wizard will appear. I don't want a clocking wizard. I'll just validate the design. Again, you can see that the value is now changed. Previously it was 99990000. That 0000 was the clocking wizard output. Okay, now I am not using any clocking wizard. So what is this frequency associated with? This is directly from the M axis mm to ss. This is the DMA thing. So ultimately it's coming from the PS, this frequency. Okay, this is the sync clock frequency that we have seen recently. Again, I will show you that once again. You look at the clocking, you can see that output clock PL fabric clock, its value is 99990005. Okay, so it's 99990005. So let's modify our clock. So how can you modify this clock? When you created the package, we have given 100 megahertz. You have to change it. Now how will you do that? Again, you have to open your temporary project. We have closed that. So I will open your, I'm going to re-edit my package. Remember, I'm going to re-edit my package. So go to your package repository, open this project. Okay, you have the option to edit packaged IP. So you go to ports and interfaces, click on your clock. So what should be the frequency parameter right now? Instead of this, go with 99990005. So the clocks will be matched. So this clocks come to this axis interfaces. That's why it was showing the error. Now you have changed the clock. What you can do? You can package your IP. Okay, finished packaging. So the IP has been repackaged. Repackage IP option is there. You will repackage it. Done. So packaging is done. So that package will be automatically updated. So we'll go to your project folder. This is the temporary. Let it be there. If you want to edit it later, you can edit. Here you can see the refresh IP catalog option appeared because it detected an IP change. So click on that. Here it will automatically identify which IP has changed. So IM underscore negative has changed. So you can simply click upgrade selected. So your IP will be upgraded. Okay. So I'm just skipping this for the time being. I'll explain that. Now let's revalidate it. Okay. So there is only one warning that is related to, you have this critical warning related to TLAST. You can ignore that. This is actually part of your access stream protocol. We are using valid, ready and data only. TLAST is optional. Clocking wizard reset, one warning is also there. You give the run connection automation, that will be connected there. No issues. Now everything is done. Okay. So once your block design is done, you can go to HDL wrapper, create HDL wrapper. So our hardware has been converted to a Verilog file which is ready to synthesis. You will have this warning. You can ignore that related to TLAST. Now go for generate bitstream. So all the synthesis implementation will be done. We will wait for it to complete. So we are done with bitstream generation. Not interested in the results and all those things, reports. I'm just closing that. Now I can export your hardware, including the bitstream. I'm exporting the hardware to my project folder. Oh, there was an error in the path. Okay, it's okay. I will save in the same location. So we actually intended to save the, we have the IM negative project. Inside that I plan to create the block design project, but it was inside this multiplier block. No problem, it's here. you can cut and paste it in that folder also. Right now you can see that your design wrapper has been created here. Okay, now once the design wrapper has been created, you can launch vitis IDE. So in order to save the vitis code in the block design, so remember one thing, you will be inside the block project right now where I am creating a vitis code. You can create anywhere, but just for I am following this pattern always. So inside this folder I will have the all file repository for vitis. Okay, so this time it is inside this vitis code. So once the vitis is launched, you can create application project. Next, here you can select your custom hardware, so which is saved in this particular folder right now, design1 wrapper.xsi. So this is my block design hardware that can perform image negative operation. Same cortex, you can give any name for your application. Create an empty project, C project, finish. So once it's done, you have to create a new C file. So in the current project, in the sources, you will not be having any C file, right? So you will create one new file. Say this is em negative. You can give any name. Okay, em negative dot em negative. This is source file dot c dot c file. So here you need a code. I have already implemented a code here. I will explain that. So you add the headers accordingly as per the need. Now here I have divided into different sections, you can see. So in the first section, in this section, you will have the variable declarations and pointer declarations which are necessary for me. So here I have an unsigned 32-bit array, its name is A. So these are the content of the array. So this is the data that I am going to transfer through the DMA to my device. So what is your device? That is the custom IP that you have created. That is your image IM negative IP. So that will read the first data, say that is 1, and it is a 32-bit data. So you will have, if you say in hex, it will be 7 zeros and 1 1, 0 0 0 0 0 1. So that will be inverted, or the negative will be taken, 255 minus 1. So you will get F 7F and 1E. Similarly 2 3 4, all these 12 datas will be read, and its negative will be taken. So it will be read as 32-bit data. We will see that when we see the result. And I am declaring an array to store the result. So B is my result. So you may see that it's 14. You need only 12, right? Because the size of this is 12. But in this DMA transfer, I will have some 2 unwanted data at the end. So if you keep 12, you will receive only up to 10. Only this array get processed. So you better keep it 14. Okay. So plus 2, you always maintain plus 2 over there. So I have already tried this code once. That's why I'm saying this. So I have a variable called status. You'll see the use of that. Now coming to this part. So this is actually important. So I have included x-axis DMA header. So if you open this header, you will get the documentation for the DMA. So how to initialize the DMA instance. So here you can see there are basically two structures to deal with the DMA. Okay, so there are two structures. X-axis DMA. This is the first structure, x-axis DMA, and the another structure is x-axis DMA config. So these structures are important. The first structure, it is saying that the x-axis DMA instance data, so driver instance data. So an instance must be allocated for each DMA engine in use. So here you have one hardware part. The second one is this structure passes the hardware building information to the driver. So this is a driver part and this is the hardware part. So you need some pointer to map into this. So focus on this thing. So the structure is x-axis DMA and this structure is x-axis DMA config. You can copy it from there. So I have already coded it here. So for the x-axis DMA structure, I am giving a name. You can give your custom name. So I have given just my DMA. So, and for x-axis DMA config, I have created a pointer. So why a pointer here? Let us look into this, because this configuration structure has to be created. So this configuration will be done using this particular function, x-axis DMA underscore lookup config base address. So you can configure the DMA. My DMA is actually this one, my DMA. So I have to configure this my DMA. Okay, you have to configure this. Using two ways you can do it. You can do it in two ways. One is using the base address and one is using the device ID. So I am doing it with the base address. You can use any method. So where I will get this function, and just copy this and find it here. See, so this is the function structure. So what are the input parameter? Input parameter should be base address. So there is another function. See, this is the other one I was talking about. So x-axis DMA lookup config. So what is the input over there? It is the device ID. So you have to identify your DMA. Where you can identify your DMA? That is from the xparameter.h. Okay, so if you open your xparameter.h, here, you just find your DMA. Okay, so here you can find the DMA ID. What is the DMA ID? It is 0. Okay, device ID is 0, or you can use this particular variable because it is defined. So right now I am using this one. This is the base address. I am copying this. So that is the base address of your DMA. So as the input base address, you can give that particular base address. That is being done here. Okay, I've just pasted it here. So using the base address, this function will perform the all necessary configuration. You just assign it to this particular pointer. That's it. So this is related to the initial work. Now you have to initialize the DMA. In order to initialize the DMA, you have to use this particular function, x-axis DMA CFG config initialize. So where you have, again, you can look at the structure of this function here. So if you look at the structure, it's here. You have input parameter. So you have the two inputs. So first one is your DMA thing, DMA instance. Second one is the configuration thing. So that was a pointer in my case. So if you look at the project, so here also, here it is asking to pass as a pointer. So it is not a pointer here, so that's why I'm passing the address of my DMA. And here it's already a pointer. What's my pointer name? My DMA config. So I'm giving that particular name. You can give your custom name here also. So this function will do the DMA initialization. So I am just using if you look at the function return type, here you have an integer return type. So what is this int? You can read the file description. So this int is actually, it will return as an integer that represents the status. So if it is, I am storing it to a variable called status. So if the DMA initialization is not success, that means if it is 0, you can say that the DMA initialization failed. And if it is success, you can print that the DMA initialization is success. That will help you in troubleshooting. You can see all these things get printed in your serial terminal. So I am just opening the serial terminal. What is serial terminal? So I'm just establishing, I'm just turning on my board, I'm just establishing the connection with COM7. Okay, you can again recognize this from your device manager, and this is the baud rate. When initialization is success, we will going to transfer the data. So what has to be done with transferring data? You want to simply send data to the DMA, right? From the DMA to the device, DMA to device, and then you have to, after processing, you have to read the data from the device to DMA. But there is another step I have included over here called preparing for data transfer. So when you try to directly transfer the data from DMA to device, and device to DMA, will end up with some errors, and this is how we can solve it. The issue is that you have to do the cache flush. Okay, so the A register has got some buffer, A array, which we have to pass through the DMA. So you have to do some DC cache flush over there, and you need to perform an invalidate range of data for the receiver also. So receiver, you can see they have mentioned only 12, even though array size is 14. I am interested about the first 12 bits, so that's why I'm giving 12 here. So what is this parameter? We'll look into this. If you look at this function, the input parameters are actually the first one is the data, that is A. Second one is the size of data. So my size of data is size of each element is 32 bit. So size of 32 bit data. So it's better to find the size of 32. So some system it may be 2, some system it may be 4. So you better use size of function and 12 into that. Or you can directly use size of A also. You can write size of A also. Here you can write size of B. If you write size of B, 14 elements will be included. I am interested only in 12. Okay, even though if you invalidate that range, that doesn't make any problem. So it's enough to keep like this. And this function, this is important for us, x-axis DMA symbol transfer. So you can see this function repeated thrice here. So this is the function used to transfer data between the DMA and your IDE device. So if you look at the structure of this function, I will show it here. You have 4 inputs. Okay, first one is your instance, then your buffer address, that will be your data, then the length of the data, size of the data, and the direction. Direction can be actually 2 parameters, x-axis DMA device to DMA or x-axis DMA DMA to device. So first thing is to transfer data A. This is the data. So this is the DMA and first parameter. Second is your data. This is the length of your data, and I am passing the array A from the DMA to device. Okay. Now what the device will do? It will do the find the negative of that data. That is the image inversion actually. It will take the negative of the image and the device will send it to the DMA. So it will be received in the array called B. Okay. So who is doing this process? My DMA. That's why here everywhere it's my DMA here. Now why I have tried to receive the data before transferring? Because after transferring, immediately he will send it back. So your DMA should be ready to receive the data. So it's always better to try a random receive operation so that your DMA will be ready to receive the data once your IP is sending the data immediately after processing. Okay, it's better to do like this. So if you try directly sending and receiving, you will not receive it properly. That's why I'm saying you just try this pre-preparation process for transferring the data. Now here it is very simple thing. You are directly sending the data. Okay, once again symbol transfer function is used to send the data. Again symbol transfer data is used to receive the data. So what data you are sending? The array A. Array A you are sending to your device. Now what device will do? I have introduced a delay of 1 second. It's not a good way of programming. We can modify it later. So after say 1 second, it may not take 1 second to process all this data. So once the processing is complete, you should receive. We will modify the code later like that. Right now, after 1 second, the device means your IM negative block. It will take the negative and send it back to the DMA. Okay, so that will be stored in the register B. Here I am just printing all the B values just to see it in the serial terminal. Okay, now let's build the project and see how it's working. So building is going on. Okay, build has been finished. So if you look at the directory there in the app, you can see the debug file. So this is the app.elf file, that is to machine language file, executable and linkable file format to dump into the PS part. And what about the PL part? So PL part need a bit stream that's already there in your hardware wrapper. Okay, so you can see all those things in the run configurations as we always do. So go to debug. Here you can see the application. Here you can see the PS file. So this is the machine language file for your PS. It will be automatically selected. And since you are programming your FPGA PL, You can see this is the bit stream that came from the wrapper file. Okay, so I'm just running it. So if you look at here, what we are expecting, once the programming is completed, the 1 to 12 array, A array will be transferred to the IP block. It will return you the inverted one. So it will be in 32-bit. I'm displaying it in hex also. So you can see the results here. See the results. B of 0. What is B of 0? FF, 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 FE. So 1 if I express in 32-bit. Okay, I will write it in hex also. So say in hex format, what will be 1? 0, 0, 0, 0, 0, 0, 0, 1. So you will have 8 hex values, right? And how we are processing that, if you remember the image negative block, that IP, where data width is 32 by 8 I was doing. So it was done in 4 iterations. That means in the first iteration, these 2 zeros will be inverted, right? Second iterations, these 2 zeros will be inverted. Third iteration, this will be inverted. Fourth iteration, this will be done. So in the first iteration, what you will get? You will get 0, 0, negative, that is FF, right? So in the next iteration, second iteration, you will get FF. Third iteration, you will get again FF. What will be in the fourth iteration? You will have 1. So 1 minus 0, 1 means 0, it's number 1 only. In decimal, it is 1. So 255 minus 1. So 250 minus 1 is 254. So 254, the hex value. Let us see the hex value of 254. So in decimal 254, in hex it is FE, right? It is FE. So you will get FE. So that's what is happening here. Okay, you will get this thing. So similarly, 2 will be FD, FC and so on. So up to B of 11, 12 elements has been successfully negative we have calculated. Now you can pass an image and try whether you are getting the negative or not. So that's all. Thank you.